Today I'm going to introduce you about our study at the University of Minnesota about the evaluation of equations to predict for the carcass fat iodine value. We all know that DDGS has been widely used in the swine diets as an economical source of energy, but also it raised the concern in the pork fat quality because when compared with pigs fed corn and soybean meal-based diets, reduced fat firmness and oily appearance of the pork belly were often observed when more than 20% DDGS were added in the diets. And the reason for this observation is that because of the high concentration of the oil present in DDGS, which is highly unsaturated with more than 50% pool fat content, which will directly affect the carcass fat iodine value. Iodine value is a measurement of the unsaturation in the pork fat iodine value, which for many years it has been used as a standard assessment of the pork belly for the many years, firmness. So therefore, for many years, most of the packing plants have set up their maximum acceptance of iodine value, which range from 70 to 74. And the relationship between feeding DDGS and the pork fat iodine value has been well established. Back into 2010, Zhu and his co-workers have demonstrated that with the DDGS level in the diets increased from 0 to 30%, the belly iodine value has been linearly increased and the fat firmness was reduced. Therefore, strategies have been developed and to predict and control the carcass fat iodine value based on the diet formulation. And one of the most commonly used approach is to use prediction equations. Three classes of predictor variables were often used. For example, the linoleic acid concentration in the diet, and also the iodine value product, which is the function of concentration and iodine value of the dietary lipid, and also the inclusion level DDGS in the diet. More recently, Pock and his co-workers developed a new set of equations in a meta-analysis which included not only the composition of dietary lipid, but also other predictor variables such as the carcass and growth performance responses, energy content of the diet, and also the feeding days. So with all these options, our question is which one is the best that we should use? So the objective of this study was to determine the carcass fat iodine value of pigs fed 8 different diets with 1 corn soybean meal diet and 7 DDGS diets. And we're going to use the determined iodine value to evaluate the published prediction equations in the iodine value. In this study, 2 experiments were conducted, and each of them utilized a total number of 432 pigs in a randomized complete block design with 9 pigs per pen and 12 replications per treatment. And the 2 consecutive experiments, the pigs were fed in the same barn with similar experimental design and physical environmental conditions. We selected 7 sources of DDGS with large variation in their oil concentration. Among these sources, we had 3 high oil DDGS, which has traditionally had more than 14% oil, and 2 DDGS contained medium oil concentration of about 10%, and we also had 2 reduced oil DDGS, which contained about less than 6% ether extract content. In this trial, 4-phase feeding program was offered, and except for the corn soybean meal-based control diets, all the other diets were formulated to contain 40% DDGS and the same amount of corn and soybean meal within phases and within that experiment. And no additional source of lipid was added to the diets, and all the amino acids and minerals met or exceeded requirements from NRC 2012. Pigs were harvested in a commercial abattoir at average body weight of 115 kilograms, and in each pen, 2 pigs with the closest body weight to the pen average body weight were chosen as sample pigs. Back fat, belly fat, and jowl fat samples were connected. And the carcass fat iodine value was calculated using the analyzed fatty acid composition and using the equation from AOCS 1998. Data were analyzed using a mixed procedure of SAS in a split block design with the dietary treatments as the whole plot and fat depots as the subplot. and also the interaction between the diet by depot was analyzed. Prediction of the iodine value was performed by each equation compared to our determined iodine value, and prediction error was calculated to evaluate the precision, which is the repeatability of the equation to predict for different sources, and prediction bias was calculated to evaluate the accuracy, which is how far the predicted values were away from our determined true value. Move on to the results. This graph shows the carcass fat iodine value of pig's fat in the first experiment. The x-axis shows the dietary treatments in the order of control: 6% oil DDGS, 10%, and 14% oil DDGS. The black line shows the iodine value for the back fat, red line shows the belly fat, and also the green line shows the jowl fat. Pig's fat, the control, had the lowest carcass fat iodine value among the dietary treatments, and pig's fat, 6% and 10% oil DDGS had reduced carcass fat iodine value compared with pig's fat, the 14% oil DDGS. And these results suggest the reduced oil concentration in the DDGS decreased the pig's lipid intake and consequently decreased the carcass fat iodine value. However, even though there was a 4% difference in the ether extract content of the DDGS A and B, pig's fat, these two different diets, had similar carcass fat iodine value, which is likely due to a different digestibility of the oil content in DDGS. Also, interestingly, we found a significant diet by depot interaction, which shows, in particular, in pig's fat control, jowl fat had greater carcass fat iodine value than back and belly fat, which was commonly observed in other studies because among the three fat depots, jowl fat has the lowest activity in the lipogenic enzymes and therefore has more direct deposition of the unsaturated dietary lipid. However, in the pig's fat, the DDGS treatments, the back fat consistently had greater iodine value than belly and jowl fat. And the reason for this observation were not very clear. For the second experiment, pig's fat, the 6%, 11%, and 14% oil DDGS had reduced carcass fat iodine value compared with pig's fat, the 16% oil DDGS. However, again, pig's fat, these three DDGS diets had similar iodine value even though there's a large variation in their ether extract content. Among the fat depots, jowl fat had greater iodine value than back and belly fat, which was contrary to their observation in the first experiment. Again, there was this trend for the diet by depot interaction which showed that the back fat had a more sensitive response to the change in their dietary lipid. For example, when the oil content of DDGS decreased from 16% to 14%, the back fat had a larger reduction in their iodine value. And this trend also applied to the change from 11% oil DDGS to the 6% oil DDGS. It has been suggested in a European study a while ago that said that the linoleic acid content was preferentially deposited in the back fat compared with the other fat depots. And since the iodine value was primarily determined by the linoleic acid content, this could partly explain the more sensitive back fat iodine value. When combined the data set from the two experiments, I reordered the DDGS treatments based on their ether extract content from low to high. The pig's fat control had the lowest back fat iodine value of about 57.7, and feeding DDGS increased the carcass fat back fat iodine value ranging from 68.7 to 82.3. If compared to the maximum acceptance of iodine value of 74, the too high oil DDGS obviously exceeded the maximum acceptance. I put the DDGS treatments into a linear regression model against their ether extract content of DDGS. This regression model showed a positive coefficient for the ether extract content, but the R-square and p-value were not significant. This means only using the oil content of DDGS is not sufficient, the single predictor of the Carcass fat iodine value, which is likely due to a relatively low and inconsistent digestibility of the oil content in the DDGS. For the comparison of the iodine value prediction equations for the backfat, in general, using the dietary IVP as the predictor variable resulted in low prediction error and bias compared with using equations using the percentage of DDGS in diet, which was not surprising because even with similar inclusion level, the oil content of DDGS is highly variable among sources. Using the POC equation, which included more comprehensive predictor variables, we had the lowest prediction error and bias. For gel fat, again, using the dietary IVP and C18-2 resulted in relatively low prediction error and bias than using a percentage of DDGS in diet. And using the Bain's C18-2 equation had the lowest prediction bias with a moderate prediction error. And using the Bain's IVP equation and the POC equation resulted in relatively low prediction error and bias. Only 3 equations were selected to predict for the belly fat iodine value, and used the Estrada IVP equation and the POC equation. Both resulted in low prediction error and bias. To summarize, by feeding DDGS with increased oil content, generally we increase the Carcass fat iodine value of the Carcass fat depots. However, only using the oil content of DDGS may not adequately predict for the Carcass fat iodine value. And in the future studies, we recommend to put the digestibility of the oil content into consideration. On the second part, using dietary IVP and C18-2 are better single predictors of the Carcass fat iodine value. And by including more comprehensive predictor variables, such as the energy content of the diet, growth, and carcass responses, we can improve the precision and accuracy of the iodine value prediction.